Hey, my wonderful AP students. This is Jock here to teach you a lot today about forces. We're going to cover the basics today. We're going to go more in depth in class. So what I want to talk to you today is about forces, angles, and tensions. This first video is to cover just the forces and a little bit of the angles part of it. And the next video, which is right coming up after this, is to cover your tension. So like I said, we're going to view the forces and the laws real quick, make sure you're okay with them. We're going to talk about forces of tension with angles and without angles. And then we're going to talk about two objects connected if we have time. During this entire time, you're going to be taking notes in your notebook. You're actually going to do one or two brief examples to make sure you know what's going on. Again, conceptual, not mathematics. And you're going to think about any questions you need to ask me to make sure you understand this. So quick review. Newton's first law. A constant velocity, or at rest, which is the same thing, will occur unless an imbalance occurs. Newton's second law. The amount of imbalance that's possible is represented by the equation ma, and the direction of the imbalance is the same as the direction of acceleration. Newton's third law. You got two objects, they push on each other, they're going to experience equal and opposite pushes from each other. We talked about non-contact forces. So far there's only one force that you know called weight. That is the force of an object from the earth, and that weight is equal to mg. So anytime something's near a planet, even if it's not touching the planet, you have this force. The rest of the ones we learned so far are contact forces. We learned that if something is touching a surface, there are two possible forces. The normal force, that's the force on something from the surface that's perpendicular to the surface. And then friction, which is, again, a force from an object, force on an object from a surface, parallel to the surface. And there's two kinds of frictions. Static, when there's no motion. And this static friction is always bigger than kinetic friction. Kinetic friction is when you're moving, and it's always opposite motion. Again, since you're moving, you want to keep moving. Objects do what they want to keep doing, and that's Newton's first law. So by definition, when you're moving, you don't want to go back to being still, so kinetic friction is always less than static friction. We have an equation. Friction is mu times the normal force, where mu is the coefficient of friction, a number, usually between 0 and 1, but it could be a gigantic number if it needs to, and represents the roughness between two surfaces. No units for it. So you try. A car parks on a hill after a snowfall. Draw a free body diagram of the forces on it if it starts to slide after it's parked. So pause this video, try to draw the forces on it. Let's see if you got them. First thing, of course, is the non-contact force, weight, pulling it down. Now it's also in contact with the surface and nothing else. So there's a surface force perpendicular. You call that the normal force. And even though there's snowfall means that it's still going to have friction. So we have a frictional force opposite the way it's going. It's wanting to slide downhill, so there's the friction force is uphill. Congrats, you just did a pretty awesome job, and this will really help you out when we start talking about forces on and angles. And just to make sure, usually I'm going to have this up here when we need to. I wrote down, like you should, the different forces and how they... Here we go. You push up at an angle on a block with mass m on a wall with friction. It goes up at a constant velocity. So since you're pushing up on it, you're probably pushing this way. Step 1, let's draw a free body diagram before breaking it up in x and y. Can you please drawing the free body diagram and pausing this for me? Welcome back. Let's see what you did. Here's the force of you pushing. Now, talking about the block, there are two things in contact with it. The surface and your push. There's also one non-contact force. That's the weight. So the surface has got a perpendicular push, that's the normal force you see here, and it's got the non-contact weight and the other frictional force down. Since it's moving up at a constant velocity, friction's opposite it. There's my picture. I wrote some stuff down. I didn't include weight though, because it makes me a bad person. I'm sorry. Now let's draw it again with the x and y components, which means this force is going away, and we're going to have an x force and a y force. I kind of added it in, but again, I forgot weight. My bad. So we can see there are 5 component forces at work here. Now, what I want you to do is please circle the x forces and circle the y forces separately, figure out if they're balanced or imbalance, and then choose a direction for positive and negative. First one I said is this. I said these two x forces are balanced because this block is not going to accelerate off the wall or go into the wall. From the horizontal point of view, it is not moving at all. So therefore it's balanced. And I find right as positive. And it's also balanced in the y. Even though it's moving up, It's at a constant velocity, therefore the forces are balanced. I define up as positive as well. You don't have to define up as positive. It won't make any difference in terms of your final result. Let's draw the angled force all alone to figure out how do you get x and y. There's my angle, there's my force. I drew in the x, which is opposite the angle, the y that's adjacent. Now we're going to create net force equations for x and y. Again, this is always situational. You don't memorize these equations at all. You always create them based on the picture. So until you interpret it correctly, there is no use in like making flashcards and memorizing every single situation because there's a gigantic number of them. So let's look at the x first. I see two forces there. Positive plus negative equals balanced. This is positive, so this positive plus this negative are balanced. The x force of my push is the opposite of the hypotenuse. So the x force is really just the overall force I pushed times the sine. The normal force is no equation for that, so it's normal. And Newton's second law says that a balanced force has no imbalance, which means ma is 0. For the y's, three forces, one positive, two negatives. That's why there's two negatives or two subtraction signs here. In this case, the y was adjacent, so I'm going to have F1 cosine theta. The force of friction is mu times the normal force, and the weight is mg, and again, they're balanced, which equals 0. So without any numbers, I've now created, and I could solve, theoretically, any value. But am I sure about that? Is knowing the mass, angle, and force that I push enough to solve for the mu? Most people would say, no, because you don't know the normal force. But even though you don't know the normal force, you could find it using the x equation, since you know the force and the angle. And then you could put it in the y as that variable and use it to find the coefficient. So if you see the same variable twice, once in the x and once in the y, you could solve for it in one dimension and use it in the other. Kind of like time for x and time for y with our projectiles. Now, before I go on to this next one, just FYI, that's what kind of AP1 is all about. You could solve for numbers if I've given to you, but there's no need to. You have the approach, you came up with the equations. In the end, it's just simply plugging and chugging, and we ain't got time for that. So let's move on. If you pushed harder, would you accelerate that thing? Take a moment and think. Welcome back. Here's what most logic would say. Yeah, you push harder means you have more y forward. Yeah, let's try that again. You would have more of a vertical force and more of a horizontal force. Since a larger vertical force will no longer be in equilibrium with the friction and weight, it will accelerate up, right? You're pushing harder, so you're pushing it up harder. The weight and friction don't change, so therefore it'll speed up. But that's wrong. Try to find the logic error in there. Pause, wait. Okay. Let's see if you found the logic error. The logic failure is that the push only changes the F1, or your push forces, and that friction and weight remains the same, but that's not true. A larger push changes the X force, but that force is still in equilibrium with the normal force. Since you can't physically push the block through the wall, more of a push into the wall means the wall will push more out of the wall, so the normal force is going to go up. And since you have more normal force, that will affect the friction, and the friction opposes the y force. So the answer is no, you can't tell. It depends on the angle. If you can imagine it, if your angle's really, really big in that last picture, so that means you have mostly up push and less into push. A bigger force, I mean you have a lot more y force and very little gain in normal force. More y force will overwhelm the smaller gain in normal force and you will accelerate up. But if you push more forward than upwards, you're going to have a large amount of normal force compared to before, which means you have a large amount of friction, and you will not have much gain in your upward force. So it could actually not only not accelerate or be in equilibrium, it could theoretically start going down, which is kind of weird if you think about it, but it's true. And with that, my wonderful students, I'll see you in the next video.